Got it? Okay, so today was a historic day in the 100-year, so far 100 years and counting, history of the quest to understand what a black hole is. And I couldn't just go on with business as usual. Had to discuss this a little bit. Now, of course, I'm talking about the dramatic images that we saw this morning from the Event Horizon Telescope. And of course, Shep came, I don't know what it was, 3 or 4 weeks ago, and told us in detail what he was, how he was going to see what they announced today. And it was very thoughtful of him to postpone the actual announcement till today, because today, depending on how many questions there are, we're going to introduce the Kerr black hole, and that's what they saw and announced this morning. And I assume the reason the announcement came today was he was keeping track of where we are in class, but the timing is very nice. So what's going to happen is we have selected, Delilah has selected a few. There was our press conference this morning and down in Washington. And of course, I couldn't get anyone from the collaboration to come in because they're all, there's a lot of, most of them are here over at the Smithsonian and the Black Hole Initiative, but today they're all down in Washington. Next week at the Science Center, there's going to be a public lecture by Michael Johnson right after class at 6. But what I'm going to do today, just to at least mark the event, is Delilah has picked out 12 minutes of highlights of the press conference. I assume a lot of you have seen it already. And then I'll make just a few comments. Maybe we'll have some questions and discussion. I asked Alex to come. He's been working on, he's our local expert in physics on all things Kerr and Event Horizon Telescope, knows more about it than I do. So we'll see how many questions there are, and then I'll go on. One more topic: surface gravity of Reisner-Nordstrom black hole that I need to cover, and then probably by the end of the lecture we'll get on to the very exciting Kerr black hole. So why don't we start the video now? I'm not quite sure how this is going to work with the microphone, but yeah, why don't we go ahead and start the video?
With Dr. Shep Doleman, EHT's director.
That's pretty loud.
I don't have control of this box, yeah.
No, that's mute. Wait, Try again now?
Okay, that's better.
That's way better.
Thank you, assembled guests, black hole enthusiasts. Black holes are the most mysterious objects in the universe. They're cloaked by an event horizon where their gravity prevents even light from escaping. And yet, the matter that falls onto the event horizon is superheated, so that before it passes through, it shines very, very brightly. We now believe that supermassive black holes, millions, even billions of times the mass of our sun, exist in the centers of most galaxies. And because they are so small, though, we've never seen one. There, though, they can outshine the combined starlight of all the constituent stars in those galaxies. The best idea we have of what they can look like come from simulations like this. The infalling gas that's superheated lights up a ring of light, where photons orbit the black hole. And interior to that is a dark patch, where the event horizon itself prevents light from escaping. The Event Horizon Telescope project is dedicated to the idea that we can make an image of this black hole, that we can set a ruler across this shadow feature, measure the photon ring, and test Einstein's theory where they might break down. It also will allow us access to a region of the universe where we can study precisely the energetics and how black holes dominate the cores of galaxies. To do this, we worked for over a decade to link telescopes around the globe to make an Earth-sized virtual dish. The aim is to, the Event Horizon Telescope achieves the highest angular resolution possible from the surface of the Earth. It's the equivalent of being able to read the date on a quarter in Los Angeles when we're standing here in Washington, D.C. In April of 2017, all the dishes in the Event Horizon Telescope swiveled, turned, and stared at a galaxy 55 million light years away. It's called Messier 87 or M87. And there's a supermassive black hole at its core. And we are delighted to be able to report to you today that we have seen what we thought was unseeable. We have seen and taken a picture of a black hole. Here it is. This is a remarkable achievement. What you're seeing here is the last photon orbit. What you are seeing is evidence of an event horizon. By laying a ruler across this black hole, we now have visual evidence for a black hole. We now know that a black hole that weighs 6.5 billion times what our sun does exists in the center of M87. And this is the strongest evidence that we have to date for the existence of black holes. And it is also consistent, the shape of this shadow, to the precision of our measurements with Einstein's predictions. The bright patch in the south that you see tells us that material moving around the black hole is moving at light speeds, which is also consistent with our simulations and predictions. And this image forges a clear link now between supermassive black holes and the engines of bright galaxies. We now know clearly that black holes drive large-scale structure in the universe from their home in these galaxies. And we now have an entirely new way of studying general relativity of black holes that we never had before. And as with all great discoveries, this is just the beginning. The imaging of black hole doesn't come easily. I can tell you that from personal experience, as can many people here in the audience. It's required long-term developments, a committed team, but it also required some very interesting cosmic coincidences. Take, for example, the maelstrom you see before you, like the hot gas swirling around the black hole. A photon has to leave from close to the event horizon, travel through the hot gas in falling to the black hole, and light rays of a millimeter wavelength, radio waves, can make that journey. Not all of them can. Then that radio wave has to propagate 60,000 years through the M87 galaxy, and then another 55 million years through intergalactic space. And then it winds up in the Earth's atmosphere, where its greatest enemy, the greatest danger, is that it will be absorbed by water vapor in our own atmosphere. So the Event Horizon Telescope uses telescopes at high dry sites so that we can see the photons that have traveled to us so far. So far, so good. We have the photons. But the M87 shadow is very, very small compared to the galaxy that surrounds it. So in order to see it, we needed to build a telescope as large as the Earth itself, given the wavelength of light we were trying to observe. And to do that, we use a technique called very long baseline interferometry, which you can see a schematic of here. Radio waves from the black hole hit radio telescopes, where they're recorded with the precision of atomic clocks that lose only 1 second every 10 million years. When you've registered these radio waves so precisely, you can then store them on hard disk drives, send them to a central facility where they can be combined precisely. It's exactly the same way that a mirror used in an optical telescope reflects light perfectly and in synchronicity to a single focus. And when we do this, we can synthesize a telescope that has the resolving power as though we had one the size of the distance between these telescopes, truly turning the Earth into a virtual telescope. All the sites that we used can be seen here. We have telescopes from Hawaii to Arizona to Mexico, to Chile, to the South Pole, and in Spain. But even this broad global network is not enough by itself to make an image. You can think of them as being silvered spots on a large global mirror. The key is that the Earth turns. During a night of observing, we are able to sweep out more baselines, more coverage of this virtual mirror to make our image. So on the left, you'll see the Earth turning. Every pair of telescopes provides us with one point on the center panel, which fills in the Earth-sized virtual lens, and on the right you see the evolving image. The more and more data we get, the more we fill in this virtual mirror, the sharper our view of the black hole becomes, until you wind up seeing what we have as the final image there. So we've taken advantage of a cosmic opportunity. It's remarkable when you think about it. Light that left near the event horizon, traveled all the way through intergalactic space, it hit our telescopes. The Earth just happens to be the right size, so we get resolving power so that we can see the black hole in M87, whose mass and distance let us observe it. And then the Earth turns to fill in our mirror so that we can make this image. It's truly remarkable. It's almost humbling in a certain way.
Thank you, Dan. It is an enormous pleasure to be with you this morning to share in this extraordinary moment. As Shep said, we have now seen the unseeable. Now, what does it all mean? Every photon in these first EHT images began its journey in a churning maelstrom embedded in the most extreme environment in the known universe, the vicinity of a black hole. In M87, the crucible in which these photons were born was powered by the black hole in two distinct but related ways. First, by an accretion flow, a violent disk of orbiting gas driven inextricably toward the event horizon. By the time the material is making its final plunge, it is crashing into itself at nearly light speed, transforming the gas into a 100 billion degree plasma. Second, through astrophysical jets, narrow beams of outflowing material speeding away from the black hole at nearly the speed of light. These jets are powered by black hole spin. Rotating black holes drag everything, gas, magnetic fields, and photons, about themselves, driving these paradoxical structures whose cosmic importance will be discussed by my colleague Sarah Markov. In M87, one of these jets is pointed very nearly toward us. The EHT images are influenced both by these bright emitting regions, the rotating accretion disk and outflowing jets, and by gravity itself. In general relativity, radio waves fall just as apples do. Typically, this effect is exceedingly small, but black holes are gravity run amok. The radio waves we see in these first images orbited the black hole before beginning their 55 million year journey toward us. This results in the dark shadow or silhouette cast by the black hole's event horizon upon the emission from the accretion flow of the jet. Importantly, the size and shape of the shadow is determined by gravity alone. General relativity makes a clear prediction for both of these features. To within 10%, the shadow should be circular, with the diameter determined solely by mass, multiplied only by fundamental constants. However, as with all voyages of discovery, when we began this expedition of the mind, we did not know what we would find. Were Einstein wrong, or the object at the heart of M87 not a black hole, its silhouette could have been very different, misshapen or missized like those seen here, or even simply missing. Changing gravity changes how light bends, and thereby changes the shape of the shadow. In April 2017, this was the dog that did not bark. The shadow exists, is nearly circular, and the inferred mass matches estimates due to the dynamics of stars 100,000 times farther away. Today, general relativity has passed another crucial test, this one spanning from horizons to the stars. The shadow is surrounded by a bright ring of enhanced emission. Oh, we'll skip this. Enhanced emission due to those photons that just escaped the black hole's clutches. The properties of this ring-like feature result from the astrophysical dramas that unfold on gravity's stage. To understand these dramas, over the past 3 years, the EHT collaboration has undertaken an unprecedented simulation effort at research institutions across the globe. This has generated the largest collection of simulations ever assembled of the accretion flow and jet launching region in M87. The southern brightness excess arises directly from near light speed rotational motions near the black hole. Regions that move toward us at nearly the speed of light are bright. Those that are moving more slowly or away are dim. From these, we have inferred the sense of rotation of the black hole. In M87, the black hole spins clockwise. Moreover, the excellent quantitative agreement between the EHT images and generic theoretical expectations of a bright crescent-like feature with a dark interior provides significant confidence in our interpretation. The object at the heart of M87, the object that powers M87's jets, is a black hole like those described by general relativity. Importantly, in combination with infrared and optical flux measurements, we can now rule out a dim but otherwise visible surface. That is, this does indeed appear to have the defining feature of a black hole, the event horizon, that point of no return. Today, several complementary windows have opened upon black holes. Science fiction has become science fact. Together, two of these windows, the EHT and LIGO, which reported the first detection of gravitational waves a short 3 years ago, have verified another key prediction of Einstein's theory of gravity. Despite varying across a factor of billion in mass, known black holes are all consistent with a single description. Black holes big and small are analogous in important ways. What we learn from one necessarily applies to the other.
Okay, great. Yeah. So I don't have any. I wasn't privy to the results beforehand. Is this thing on? I wasn't privy to the results beforehand. There's apparently some papers coming out today with the details. So I don't know much more than what you heard, but there were a couple of things that really caught my attention. So they undoubtedly know the answers to this, but they haven't told us yet how it works. So it's not quite, it looks like this. These two bright spots down here. Now we know that M87, so these were things I'm just wondering about. This is the glowing in here, and it's really glowing here and here. And the black hole in M87, they already know has a jet spouting out of it, a huge, powerful jet. My understanding is that most of the emission from the jet is the wrong frequency. I mean, that's a good thing, right? Because the jet emits so much stuff that if you tried to look at the black hole, it would just be drowned in the signal from the jet emission. So they're looking at a frequency where there's the jet is ultra relativistic, so I think it's mostly. Do you know what the frequency is typical?
They talk about gamma factors of 10 to 1,000. So.
Okay. Anyway, it's higher than what the EHT is seeing, so that's I guess part of why they chose it. And there's something like 15 to 20 degrees between the line of sight that we're looking at it from. We're looking at it basically from on top, right? But not quite on top, 15 or 20 degrees. So that might explain why, you see, if it were a perfectly round black hole, there would be no reason a Schwarzschild black hole, which is the kind that we've discussed, there would be no there would just be a symmetry. There would be no reason to it for any one angle to look any different than any other. But what I'm assuming is that, and I don't know which way, that there's a little vector here, which is this vector, the angle between the spin axis and the line of sight is probably pointing either down here or up here. And so if there's stuff swirling around like this, it will be, when it gets on one side, it will be more blue shifted. On the other side, it will be more red shifted. And they're only looking at a fixed frequency zone, so that could account for why it's thicker on one side than the other. I'm just winging it here. These people certainly know the answers to all these questions, and they simulated it on their computer, last year. And the other thing that caught my attention was the statement, I don't think it was on there, but I heard it this morning, that they know it's going clockwise. I don't know how they figured that out, that it's spinning clockwise as you look down on that. Because the period should be days or weeks, and on how fast it's, and I don't know how they can tell that from. You certainly can't tell from that photo, because something which is spinning counterclockwise is the time reverse of something which is spinning clockwise. So there's no way from a photo that they showed of at one instant of time that you could possibly know. You might be able to deduce from this thickness that it's spinning, because it looks different on one side than the other. But there'd be no way from what photo that you could know whether it was going clockwise or anti-clockwise. So obviously they have a lot more information than what they than what they've announced this morning. Yeah.
If I had to guess, because in some of the examples they were talking about looking at the when Avery put up that big picture with all the different spinning simulations, I guess because there's slight variations in the density at different points in the disk, you could get like these bright flares that go around, and so maybe it's from the different days looking at where that bright spot is, whether they got the direction. I don't know. That's just a guess.
Yeah, that's a good point. Maybe those bright spots are moving.
Yeah, because I think the image they're showing is the composite, right? I think the big one they've been showing is a composite of the different days of the data. I think.
Yeah.
And then secondly, since it's right around the bottom and that has to be coming towards us, okay, if it's spinning clockwise, my guess is we're slightly off angle this way.
It could be this whole
Right, this
lobe
whole
be
thing was
going
probably-
around. I don't know. What? Yeah.
Right, it's probably
Yeah,
coming
because
towards us, and
it's
it's slightly,
actually-
because this is brighter because it's coming towards us, or I guess for you, this way. Like
Yeah.
you're talking about it.
Like the little arrow picture, right?
Well, or I was thinking it would be from what Andy drew, where he drew it going from us to the axis of symmetry would be what he drew but flipped. So from the center of the picture slightly upward. Because I assume the spinning towards us stuff is the stuff that would be kind of curled towards us slightly off axis instead of being perfect range.
Hold it this way.
Speak louder so everybody can hear. If you're gonna say anything, you have to say it loudly.
Okay.
Especially because we've just got a feeble microphone here.
If my pencil is the axis of rotation, and we start by thinking about the one where the jet is hitting us, and then it's going clockwise, then the top and the bottom are downward shifted relative to us. But if we move it to the right a little,
Right.
when it comes along the bottom, then that's going to get downward right, and then the top.
Right.
Top.
Right. 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 And that will affect the luminosity in two ways. One is it could move things out of the frequency range, in and out of the frequency range of detection, and also I guess the intensity of the missions might depend on that. Yeah. Comments, questions? There was one other funny thing, I don't know if anybody caught this, but there was, didn't they say something about things moving at the speed of light? What was that?
I think they were talking about the Photon Orbit.
Well, they were talking about photons moving, not the horizon moving at the speed.
I thought they were just
Maybe
saying the
I
gas
thought
is
the
moving
gas
close
is
to light
accretion.
speed. Not that it's literally moving at the speed of light.
What did
I
they
thought
say?
I thought they were just saying the gas was moving close to light speed near the horizon, not that it's literally moving at light speeds.
That's fine.
That's how I interpreted it. Like as the gas falls in, it accelerates to
But
near
the
light speed.
infalling gas,
Yeah.
not the co-rotating.
Yeah.
That's probably what they meant. How about a question for Alex? I dragged him in here.
I was thinking of explaining what the shadow is.
Okay, go for it.
Because, I mean,
Take this.
Okay, I just. Okay, so this is a little unprepared, but I just thought since everybody today is talking about the Event Horizon Telescope, which perhaps should be more appropriately named the Shadow Telescope, because we're not seeing the event horizon, we're seeing the shadow. And in fact, this feature on the image, let's put the image up here since we have it now. So supposedly this dark patch is not the actual event horizon, but it's the shadow of the black hole. So what is the shadow? And maybe this is jumping the gun a little bit because Andy's going to introduce the Kerr Metric today. But the existence of the shadow is a direct prediction of the Kerr Metric. And if you study the propagation of light signals in the background of the Kerr Metric, which is something you'll be able to do at the end of this course, you'd be able to follow along the derivation of the shadow and get a precise formula for its shape as a function of how fast the black hole is spinning and what angle you're looking at it from. So I'm not going to go through the derivation because that would be jumping the gun, but maybe I can just show the formula, and so at least you'll have a formula for the shadow, which was measured today. Why is there a shadow in the first place? What do we mean by this? Okay, so maybe this is a little, this was not obvious to me. Yeah, maybe let's start very basic. So we have this intuition, because we live in flat space, that when we see something somewhere, it's actually there. And so physics is, it's a long journey of forgetting, unlearning what you have learned. And so the first thing we have to forget is that when we see something somewhere, it's not necessarily there. So this is really a story of two pictures. One is the real picture that we actually see in the sky. And then the other picture is, what's actually there in physical space. And I think, you guys, everybody saw the announcement this morning, but by studying the Kerr Metric in this class, you get to see the other picture that tells you what's actually there, not what you see. So what's actually there? Well, there's a Kerr Metric that describes a black hole. And black holes in astrophysics are typically spinning, so there's an axis around which they rotate. And we typically draw the event horizon as a sphere, but since this is a GR course, I think it's very important to emphasize that unless the black hole is not rotating, which is like the Schwarzschild metric, where there's really spherical symmetry, in general, the event horizon is in no sense spherical. If you look at the induced metric on its surface, it's not a sphere. But in the coordinates that we choose to write down, the coordinates that I'm sure Andy will use, you'll use Boyer-Lindquist coordinates, the event horizon is a surface of constant radius. But you could always do a coordinate transformation and make it whatever shape you want. So this is a cartoon, but it's a very useful cartoon. And typically what we think happens in the real world is that there's a black hole, and there should be matter that accretes around it. So just like the moon orbits the sun, the Earth and the Earth orbits the sun, there can be matter orbiting this large object. And typically we expect there to be a matter disk of matter that's swirling around or accreting onto the black hole. So this is known as the accretion disk. And different black holes have different accretion disks for some black holes we can't see one, for some of them we can, and it's thin, for others it's thick or puffy. So there are different configurations, but that's one element of the story that you need to add on top of the Kerr metric that describes the black hole's space-time geometry. And then there are also magnetic fields. And I think one thing that's very exciting about the Event Horizon Telescope, which we did not hear about today, but this is looking ahead to the future, is that I think, okay, so I'm not in the collaboration, so what I say is not binding, but I think they'll be able to see not just the brightness and intensity of the light that comes from this region, but also its polarization. And that, we think, will be related to the shape of the magnetic field lines that are around the black hole. So in fact, we think the Event Horizon Telescope will be able to infer what magnetic fields there are around the black hole. So that's also really exciting because it's not a feature of the Kerr space-time per se, but of electromagnetic fields also in this crazy regime. So there are magnetic fields, and there's an argument which goes back to the 70s by Blanford and Znaik that these magnetic fields, obey some equations known as force-free electrodynamics. And as the black hole spins, these magnetic field lines get spun up around the axis, and they can extract energy from the black hole. So these jets that we saw in the simulation that was shown, they're the most powerful light signals in the universe. They have these like very thin, narrow beams of light that can stretch over millions of light years. People for a long time were confused as to what could possibly power such a collimated beam. It's like a laser beam of light. And the accepted explanation today is that it's a so-called AGN, or active galactic nucleus, which is what you call the black hole when it has these magnetic fields that power jets. And it's at the center of a galaxy. So when you have this system at the center of a galaxy, we call this an AGN, or active galactic nucleus, and M87 is an example of that. And I'm going to speculate that the reason we got the picture of M87 first, rather than Sagittarius A star, which is the black hole at the center of our own galaxy, is probably that this black hole has jets and is much more active, and this is tied into the spin. So when the spin increases, there's more energy that can be extracted. The jets are more powerful. So it's likely to be more rapidly spinning. Okay, so this is the lay of the land. This is what's actually there in physical space. And in principle, we believe we know the equations that describe the physics around here. So we think the Kerr metric gives you the space-time geometry up to the event horizon. I'm not going to speculate about what's inside. And there are magnetic fields. We think we know more or less the equations that describe them. There's accretion disks. But again, we think more or less how to describe all these elements. And now the question is, how do you turn this into a picture? And as I said before, because space-time here can be very curved, what you see is not necessarily what you get. So this picture is meant to illustrate this. Now, suppose I had a basketball here, and I had a screen behind it, and I had a very powerful flashlight, and I shone a bunch of light. Then the light rays would go along, and a few would hit the basketball, and the rest would just pass above, and it would cast a shadow. And so here on my screen, there would be a dark patch, which is the shadow cast by the silhouette of the black hole. Now, sorry, of my regular ball. Now, if this is a black hole, then the same idea applies, except because gravity warps space-time, the black hole has a gravitational pull that can bend the light rays. And so in particular, the black hole is a little bit greedy. It can sort of has a reach, and it can grab the light rays that are passing around it and pull them in. And so this is what's depicted on this figure, which is roughly the same plot. So here you can imagine that you're holding a flashlight. We're looking at the black hole from above. It's spinning around this axis. And somebody's to the side shining a flashlight, and there are many light rays. The ones that are aimed directly at the black hole fall in. The ones that are aimed far away get deflected, but not very much. And then there's a boundary impact parameter. There's a special place where if you shine the light, it just glances the black hole. So if you shine it a little bit higher, it gets deflected but escapes. If you shine a little bit lower, it gets trapped and eventually falls into the black hole. And there's a special place which is delineated by this green line, which is known as the photon orbit. And it's the boundary between where light is trapped and where light can escape. And so in the Kerr metric that Andy will write down, you can study the propagation of light in that background by studying null geodesics. And there's a special radius known as RPH, where pH stands for photon orbit or photon sphere or photon ring, which is this green place. And it's a place where there exist spherical circular orbits for light. So light can go there and just kind of go around. It's not on the event horizon. So the event horizon is the place where nothing can escape from. Here things can escape, but light can stay trapped for a very long time. And because it's an unstable circular geodesic, eventually it either falls in or comes back out. So the expectation, I think before we even saw this picture, that's why people talked about the black hole shadow, is that if you have a bunch of backlighting, so this is what happens in physical space. Now let's connect these two pictures. This is what happens, really, really there. You put a coordinate chart and you say what happens in each coordinate. And then this is what you actually see. And so the connection between them is that we think there are jets, which are bright. I'm not actually sure what's on the image. I haven't had the time to digest yet, but whatever is shining could be hot spots in the accretion disk. They could be bright. This is a very violent place. It's very hot. There can be nuclear explosions. The matter here thermalizes and radiates. So whatever light there is, you can just think of it as backlighting. This light goes around, and then some of it will just fall in. Everything that's within here falls in. But a lot of it will escape, and the boundary between these two things defines the edge of the shadow, right? So the black hole will pull in some of this stuff, but there will be a last place where things get pulled in, and then this last place defines the edge of the shadow, which is what we're seeing here. Does that make sense? Okay. So maybe I can write down the equations that define the shadow. Is that a... Sure. Okay. So how do we describe all of this in equations? Yeah, I think it's good to have a few extra equations because everybody's saying the same things, but since you know general relativity, we can actually write down some things. So the way we describe images of a Kerr black hole is by studying the propagation of light in the background of this Kerr geometry. And so we're studying null geodesics, which describe light rays. And a photon, or a light ray, in this Kerr spacetime is described by two parameters. They're usually called lambda and q. And they're conserved. So they're conserved quantities for the photon. What are they? One is the angular momentum ratio to the energy. And the other one is something called the Carter constant and its ratio to the energy. And actually, I should put a square root here. So these things have technical definitions, but the point is when you write down the geodesic equation that describes a particle in this background, you can see that you can define an energy, which is the momentum p mu of the photon obeying the geodesic, dotted, say, with minus dt. So this would be the energy. Then the angular momentum L would be d phi mu p mu. Okay, of course this doesn't really make sense because I haven't told you what the coordinates are, but when Andy writes down the metric, there will be a time and a phi metric, and this is what I mean. And then finally, the Q is actually a little bit more complicated, so I'm not going to define it. But the point is that there are these two parameters that parameterize the geodesic and that are conserved along it. So that shouldn't be too surprising or hard to believe. And these parameters tell you where you see a photon when it reaches you. So suppose that you're an observer looking down, say, at M87. So you have a line of sight to the center of the black hole. For the case of M87, we think the angle from the spin axis is about 15 to 20 degrees. But we're going to write down a general equation, so let's call it theta observer. And what you should think of your photographic plate as is perhaps best shown with this picture. because it's worth 1,000 words. So this is what I have in mind. So we're here, and we have a line of sight to the black hole, and we can imagine the plane perpendicular to the line of sight. And then if a photon, say that's emitted from a backlighting source, this would be the flashlight behind the black hole. If it emits a light ray, maybe the light ray gets deflected by the black hole, and when it reaches you, it comes at you from a certain direction. Now, given that it comes at you from a certain direction, you might say, the light ray came at me from that direction, so that means the object that it shown that light is over there. And so you would say this light ray came from this point on my photographic, on my screen. But in actuality, maybe it came from there. So this is where you have to be careful. What you see, your eye would tell you, you saw this dot over here, but actually it's over there. And now let me just sketch a few equations. So the relationship between these conserved quantities, which are the impact parameters of the light ray, and where you see them on your screen. So if your screen has a coordinate alpha and another coordinate beta, beta is just the projection of the axis of spin of the black hole onto the plane perpendicular to the line of sight. So there's a relationship, which is alpha is minus lambda over sine theta O, and beta is root q squared plus a squared cos squared theta minus lambda squared cotangent squared theta O. So here theta O is the angle of observation. And this formula, what it's telling you is that given a photon that reaches you with these conserved quantities, energy, angular momentum, and Carter constant, these are impact parameters which translate into an image on your screen that has coordinates alpha, beta, given by this formula. Okay, so now the only thing I need to tell you is, all right, there's a screen, alpha and beta. My black hole, I should say these coordinates are defined such that the true location of the event horizon, so where you would see the event horizon if light traveled in straight lines, if there are no gravity, is normalized to 1. So this is radius m. Well, we're using units where the event horizon is size 1. And then the thing that remains to be said is, what is the shadow cast by the black hole? So I told you that just like a ball, which is a spherical object, casts a circular shadow, a black hole, which is a more complicated object, casts a more complicated shadow. And the shadow happens to be circular most of the time, or almost circular, for most angles and for most spins. A here is the spin of the black hole, which has mass m and angular momentum j equals am. And these are the two parameters that will appear in the Kerr metric. And so the last thing I should show you, maybe I'm not sure, maybe it's too technical to write down, but let me just plot it for you. So this formula here, if you care to write it down, you can. It's 8.2. Maybe I'm not going to write it down. It's too complicated. But this formula parametrizes the shape of the shadow on your screen. So this is lambda and q. So there's a curve on your screen, which is the shadow of the black hole. So this curve you can write as lambda of r tilde in my parametrization, q of r tilde. And using these formula, that gives you a parametric curve alpha of r tilde, beta of r tilde. And the equations for this parametric curve are given here. And r tilde, which is the last thing I have to tell you, the parameter along the curve, which traces out the shadow on your screen, has to range between these two radii, which are the physical radii in Boyer-Lindquist coordinates of the photon sphere, that green ring. And there's a plus and a minus because there's a photon sphere for photons that co-rotate with the black hole, and then there's a photon sphere for photons that counter-rotate. These are called prograde and retrograde. So there are two photon spheres, depending on whether you're going around with the black hole or not. These two photon spheres have these two radii. And because the shadow is set by the physics of this photon ring, it turns out to delineate the curve that you trace out in your screen to get the shadow. So to do the derivation maybe before you've seen the Kerr metric is premature, but I just wanted to show you that this is what has been seen today. So if you take a black hole like M87, which we think is rapidly spinning, the way they inferred the mass, you can put in some parameters. This, unfortunately, if you trace out this curve for various values of A, it doesn't really depend. The size of the shadow shape that you get on the screen doesn't depend too much on the spin. So the first thing you can say is just from the shape of the shadow, we can infer the mass, because the overall scale does depend on the mass. And when Shep in the video said we can measure the shadow and put a ruler across it, if you can see the diameter of the shadow, it's using this formula, you can infer the mass of the black hole. And I think that's how they were able to say how big it is. OK, I talked a lot. Maybe I should stop here. Yeah, question.
What does the shadow start to look like when you approach the plane of the disk? For theta goes near 90.
So for most values of the spin parameter and most observation angles, the shadow is, to the naked eye, looks like a circle. It's a fun exercise to take your favorite plotting software on your computer, maybe Mathematica, and just this is a parametric curve. I just gave you all you need to plot it. And then you can start to play with the parameters and say, suppose I'm at this angle, what shadow do I see? What shape does it have? And so forth. And so most of the time, it basically looks like a circle, but that's not what I drew here. So there's a special corner of parameter space, which is very dear to our hearts here. And a couple weeks ago, Andy talked about rapidly spinning black holes and how they can be viewed as a critical point in astronomy, et cetera. So the case where the black hole is maximum. Later. But you mentioned it 2 weeks ago.
Oh, did I talk about the spinning one?
You talked about critical points. So, OK, so I will restrain myself, but I'll just say this, that when the black hole spins very fast, there's something qualitatively very different about it. And because this course respects causality, we'll get to it later. And the observable features of the black hole, including its shadow, have very peculiar properties. And we're hoping there are other peculiar features which could be observable if M87 is spinning fast enough. But the striking one is the shape of the shadow, which if you're within a cone of about 90 degrees here. OK, I should have drawn a right angle. Pretend this is a right angle. So more or less, there's an opening angle of about 90 degrees around the equatorial plane. And if you're looking at the black hole from within this region, then you would see a shadow. And again, this isn't the case where the black hole is spinning very, very fast. You would see a shadow that's not a circle, but actually has a flat line here.
By the way, just to interject one comment, I think Avery Broderick should be. I think he kind of said that the size of the shadow depended only on M. He certainly knows this formula, which also involves this spin. But he was simplifying for 10 billion people watching or whatever. But
Yeah, that's
it wasn't quite right.
yeah. It is a small corner of parameter space. Maybe he just doesn't want to emphasize it. So there are thousands of things that could be said. Maybe I can just flash you.
You've got an urgent question.
Sorry, question.
Sorry, I have a question. So when we look at these, we usually pick a coordinate system to do the calculations on.
Yeah.
How do we know which coordinate system is the one that we actually see? Because you can choose all sorts of weird coordinate systems that are just kind of weirdly looking rulers, more or less. But we have an intuitive coordinate system that we view things at.
Yeah. So in general relativity, whatever physical observable you compute had better not depend on your choice of coordinates.
Yeah, but I mean, for
Yeah.
example, if you pick one coordinate system, then you could say if it's very small. I guess what I mean is that if we're measuring things with a ruler, right? That's a meter large. Let's say I could pick a ruler that that has a log scale, right? So it decreases in length as you go along the length of the ruler, and that's like what I intuitively see. But when I write down a coordinate system, it's not obvious which one is the intuitive one.
Yeah, so let me say first, there's no need to worry. These equations have the property that they do, whatever you compute, if you say I see a dot here, it doesn't depend on the choice of coordinates you use. But of course, in defining these Lansing equations, I said you project down the line of sight to the plane perpendicular. Secretly, I mean, the reason we're doing that is because those equations are supposed to turn what you see. There's what really happens, like the photon can bend, but then when your eye sees, it doesn't know that. So these equations are, when you derive them, you basically have to ask the question, if I get a photon with these impact parameters, where would I see it if space were flat? I mean, that's because when you think of a lens, space is flat inside the lens. So I'm not sure that's addressing your concern, but the point is, the definition of the screen and its coordinates is such that it's designed to answer the question, of course space-time is curved and these light rays can be deflected, but given that I get a light ray from an angle, what would I see if it had come from some ray propagating in flat space?
Yeah, but if we're going around the black hole, we're not in a, like for example, if you take a Schwarzschild black hole, there's like cross-coordinates that look more or less flat. But like we're not in the coordinate system that we see wouldn't be cross-coordinates because we're in a rotating frame.
That's true.
So like how do you know what the relationship between those coordinates are and the coordinates that we actually see are?
Yeah, so it's important when you define these things that you be very far away from the black hole, where space-time is asymptotically flat. So if you were in anti-de Sitter space, which was mentioned in this class before, which is a gravitating box, then I don't think the derivation that leads you to these equations would apply. So there's an important step here that you say I put my observer, my photographic plate or my screen, whatever, is very far away, where the curvature space is very low, and I'm approximately in flat space. And in fact, to derive these equations, you have to sort of identify the coordinates where you are in the Kerr metric with sort of coordinates where you would be if you were in flat space. And then you would say, given that I got a photon with these impact parameters, where would it have come from if space had been flat? Which is what, remember, this picture, a picture is worth 1,000 words. Did I close it? So in this plot here, the actual object is over there, but the coordinates over here are defined so as to show you the image of the object where you would have seen it if the light ray had propagated in flat space. So the object is over there, and on the screen you don't see the object where it is. You just see it where it would have been if the light ray that you got from it had always traveled in flat space. So this identification has to be made at very large distances. Yeah.
So on that beautiful picture, is it clear what is the Schwarzschild radius?
Well, okay, so I think that the day that the discovery is announced, I think nothing is completely clear, but I think the claim that they're making is that this is the size of the shadow.
Yeah, that looks reasonable.
So the Schwarzschild radius is like a fifth of
Radius
that.
is like quarter one, like half of that.
You're asking how big the shadow is. So I gave you the very complicated, precise answer with that equation, but let me give you the simple answer. So if you look at the black hole exactly from above, and for M87 we're slightly off axis, but to a good approximation this is true. Let's say you're exactly above, then the shadow is perfectly circular. Then it's precisely mathematically a circle because there's axial symmetry. Nothing breaks that. And in that case, the size of the shadow if the black hole is not spinning at all. So if you're in Schwarzschild, where there's no spin, the diameter of the shadow on your screen would be 3√3 m, which is about 5.2 m. And the Schwarzschild radius of the horizon in that case is 2m. And if the black hole is maximally spinning, then the location of the horizon shrinks from 2m to m as you spin up the black hole. And the size of the shadow goes down to 2 times 1 plus root 2 m, which is about 4.8 m. And I don't go around knowing these numbers off the top of my head, but I just looked them up today. So I'm not a robot. If you ask me tomorrow, I won't know anymore. But
So in principle, it's some like not really tiny, but you can.
yeah, so I mean, I love. Yeah, I love that Shep used the word ruler. He said we can put a ruler and measure the black. So, you know, I like that image. You put a ruler here, and the length, the distance that you measure is, well, it doesn't really matter. It's 10 m. That's the diameter. The point is, independently of the spin, it's about 10 m. And certainly you can see the image is a little bit blurry. So, you know, to the precision that they have, you can just say it's 10 m. It doesn't really matter what the spin is. And of course,
So the black hole,
yeah.
Avery said that their observation is consistent with that inner circle there being a completely sharp line, right? And it's fuzzy on the picture just because they have limited finite resolution. So we can kind of eyeball that, see how much resolution is, and it indeed looks like the extent of the fuzziness is about a tenth the. So that would be the size of one pixel. Would be the. You know, if you look right here, where it goes from clearly orange to clearly black, that's about a tenth of this. That was what they said in the press conference, that the resolution was about a tenth the size of the shadow. I mean, it could be that if they increase their resolution by a factor of 1,000, this will suddenly become one really sharp line. And but according to that formula over there, that fuzziness is about the size that we'd expect a black hole to be.
Yeah, and I was looking at the paper, and of course, you know, if what they measure is angular size in the sky, so they measure this angle theta, and of course the actual distance has to be multiplied by, to get the actual scale, you have to multiply the angle in the sky by the distance to the black hole, and so to say what the mass is, they claim a measurement of a mass of about 6.5 billion solar masses, which is, I think, a little bit higher than the estimates that I was reading before. But there's uncertainty in the distance to the black hole. So I think it's not completely sharp. But in principle, if you knew exactly the distance to the black hole, then you just literally put a ruler and measure the mass of the black hole with your ruler, which is pretty cool.
More questions for Alex?
Yeah, it can happen. I mean, you can have. Yeah, if you think of a Schwarzschild black hole, which is not rotating, you can have geodesics that have some initial angular momentum around some axis of symmetry, and they'll keep on rotating.
So we wouldn't see something like this in that dimension, right? Where all the,
Well, a very interesting aspect of. So I think not quite related to the Event Horizon Telescope is a question of how do we even tell what the spin of a black hole is. So there's a list of black holes in the sky for which we think we know the spin. And you might ask, why is it that we know that? And in all the models that people write down, it's assumed that the last place that you get light from is the last place where there's a stable circular orbit. So in the actual world, okay, there are different models of accretion. There's fast accretion and slow accretion. And what people mean by this is every particle that orbits around the black hole has some radial components to its motion, which is the, how fast it's infalling, and then it has the orbital motion. So in the case where the black hole is slowly accreting, then to a good approximation, all the orbits, all the particles in the disk can be approximated by circular geodesics. Of course, over time they drift inwards a little bit, but to a good approximation, they're circular geodesics. And the best, to my knowledge, the best theoretical model of accretion that's been written down was written down in the 70s by Novikov and Thorne. And the original place where it was published, I think it takes 100 pages to discuss what the model is. So even though it's the simplest model you can write down, where it's an equatorial disk, which is completely thin, equatorial, and they also assume fairly slow accretion, so that everything is basically on circular orbits. To sort of follow through all the consequences of the physics in that disk takes them a really long time, and it's incredibly intricate, and probably the best you can do by hand. At some point, you just have to go to the computer, and Avery Broderick that was talking just before, he knows how to have very puffy disks with all sorts of things happening. But I can tell you in the simplest case of slow accretion with a thin disk, which is the case we can discuss analytically, there it's a good assumption to describe particles by circular geodesics. And so then, the properties of, there's always a small radial infall component to the motion, but it's a very small inward velocity compared to the orbital velocity, which, by the way, as the black hole spins up and you get an orbit that's closer and closer to the event horizon, well, I think, Andy, you're probably going to do this, but the particles start to, they become more and more forced to co-rotate with the event horizon. And the event horizon, at maximal spin, these particles can be very close to the event horizon in some suitable sense, and in some sense they have to go very fast almost at the speed of light. Okay, all these terms have to be defined carefully with equations, but yeah. So maybe just did that answer your question? So in general, things are not on geodesics; they're not in free fall. They can be accelerated, but if they are geodesics and the accretion is slow, then they're pretty much circular geodesics in the equatorial plane at least. And then we can just solve the equation that describes the motion. People have done that, and you can say a lot of things. There's a special geodesic which people talk about a lot, which is known as the Isco, for innermost stable circular orbit. That's the last radius at which a particle can just stably orbit around, and once it falls into a smaller radius than this Isco radius, it just has to plunge in very rapidly. And so I said earlier that this accretion disk can be a violent place. Typically, as you approach the inner edge of the disk, which terminates at the Isco, because beyond that, things just fall in very quickly. As you approach the inner edge of the disk, the disk is never completely thin. There's always some vertical motion, and that is such that at the inner edge of the disk, at the Isco, the particles kind of get pushed into each other, so they're very hot. And there's a lot of radiation that comes out of here. And it turns out that unlike the size of the shadow on your screen, which is not very sensitive to spin, the radius of the Isco varies a lot more with spin. So for instance, when the black hole is not spinning, you're in Schwarzschild, the Isco radius is 6m. And when the black hole is exactly spinning, it's exactly at m, which appears to be on top of the horizon, but not quite. I'm sure Andy will talk about this. And so the Isco radius varies quite a bit with the spin. And moreover, not only that, but every photon that escapes the vicinity of the black hole, so of course within the event horizon nothing can escape, but if you're slightly away you can escape, but you have to climb out of a gravitational potential well. And as the black hole spins up and the Isco gets closer to the event horizon, it's sort of deeper in this gravitational potential well, so you can think of the black hole as a hole, and then the Isco gets closer and closer to the event horizon, and so it costs light more and more energy to escape. It has to pay a toll to get out, and so its energy is proportional to its frequency. It loses energy to escape the vicinity of the black hole, climb out of the gravitational well, so it gets redshifted. And so I think the best known way to measure the spin of real black holes in the sky is to look for accretion disk emissions. So as I said, the matter in here is pretty hot. It radiates, and there's iron atoms in here. So you should be able to look at the spectral lines. You should look at the spectrum of radiation that you get. You should be able to identify the iron line. I mean, there are many iron lines, but there's one that's particularly bright for the kind of physics that occurs in the disk. It's called the FeK alpha line. So that's this particular iron line that's relevant for accretion disk physics. And the point is that you shouldn't actually see a single line, but you should see a broadened spectrum, because there are iron atoms here, iron atoms here, iron atoms here, iron atoms here, all the way to the Isco. And so the closer you get to the Isco, the more the emission is redshifted. And so instead of getting a single line at that fixed frequency, you get a broadened spectrum of emission. And the most redshifted emission comes from the light that is closest to the event horizon, which is basically the Esco, because everything beyond that falls in quickly and doesn't radiate very much. So by looking at the most redshifted iron line in your spectrum of emissions we see from a black hole, you ought to be seeing say the emission from the Esco. And so the redshift sensitively depends on the position of the Esco, which sensitively depends on the spin. And so from measuring the redshift of emissions, you can tell what the spin of the black hole is. So that was maybe a lot, but does that make sense? Yeah. I'm not privy to any special information. I have a guess.
Yeah, okay, what's your guess?
Well, I think, so the physics that describes these jets is not completely understood. It's a very complicated physics, but one thing that we do seem to know more or less for sure is that the amount of power radiated, the amount of light that you get from an AGN seems to be correlated with the spin. So black holes that spin more just seem to shine more light. So that could be a reason. Another reason is that, this black hole M87 we're looking at from above. So maybe there's fewer things in between, because most things that orbit, they tend to stay near the equator. So maybe the disk is thin, or maybe it's puffy but still tends to be equatorial, whereas near the pole maybe there's fewer things obstructing it. And in general, for Sagittarius A star, we're in its equatorial plane because we're in the galactic plane orbiting around it. And so there's a lot of matter in between. There's the entire galaxy. So I think a mixture of these things I would expect is the reason. So maybe it's just dimmer because it's not spinning as fast, or maybe it's not dim, but there's just a lot more noise separating us from it. But I think when our friends from the EHT come back, now that the cone of silence has been lifted, we'll be able to grill them and get really more precise answers.
There was a similar question during the press release, and I think the main response from one of the experts was that there's much faster time dependence for Sag star.
Interesting.
Yeah, you can't use as much data to get one picture.
Interesting. Yeah, so just very basic dimensional analysis. Okay, let me say maybe this last thing, and then I think I've spoken a lot. So let's just give a few numbers. And I think this is actually the coolest thing about this discovery, because I realized, I've been thinking about this for years, and we hear about these EHT things all the time. But seeing it, the public announcement today and seeing my friend's reaction when the phone was beeping the whole day, it actually forced me to see it as a new thing, anew. And the sheer excitement and wonder of it. I mean, Shep said that the black hole has the same size in the sky as a quarter in LA as seen from the East Coast. So there are many such analogies. The one I like is that these two targets, which are the biggest black holes in our sky, have the same size in our sky as an orange on the surface of the moon. So suppose somebody's holding an orange on the surface of the moon, you have to take an up-close shot of that. And another one I read in the news, everybody's coming up with their own analogy. Obviously, you can do this infinitely many times, but each one I think brings, really hits home again. So another analogy is that it's like trying to take a picture of a single grain of sand on a beach from an airplane flying at high altitude. So I think, all of these things are the same statement, just, rescaled. But depending on which scale you use, it's more or less impressive. So this last one is very impressive. So the two black holes are Sagittarius 8 star, which is 26,000 light years away. It has a mass of 4 million solar masses. And then M87 is 50 million light years away, which is about 2,000 times more, but it's also about 2,000 times bigger. Okay, not 8 billion, but 6, 7 billion solar masses. And by the way, this is something, I guess you'll see this, but the size of a black hole scales with the mass. And this is something that I think does, requires you to pause and really think about it, because usually if you have an object like a ball, which has some fixed density, and you say, I'm going to double the radius of the ball, then the volume grows by a factor of 8, right? So the mass of the ball, you would say, assuming constant density, would have gone up by 8. So black hole is not like a regular object at all, because if you double the mass, you also double the radius, which means you multiply the volume by 8. With a regular object of fixed density, if you multiply the volume by a factor, you also multiply the mass by that same factor. Whereas here, you multiply the mass by a factor, the volume increases much more. Well, okay, yeah. So if you study more physics, you'll see that there are good reasons to suggest that you shouldn't expect the volume scaling anyway. So I'm not going to say this, but the last thing I wanted to say is that you can take these masses and you can do dimensional analysis and turn them into time scales. So if you ask what is the characteristic length scale, well, it's just this M. So let's call this MA star. Let's call this M87. So you can use factors of G and C to turn masses into distances or time durations. And so the characteristic time scales associated with these masses are, so this mass in units of time is about 5 hours, 4 to 5 hours, 5 hours. And then this is 2,000 times less. So okay, seconds, minutes, 1 hour. Yeah, I guess on the order of seconds. Okay, I'm going to say something stupid, but
It's 1,000
yeah,
times shorter.
1,000 times shorter. So
2.5
minutes.
The shortest time scale with M87 is 2.5 days. So it becomes like, like an hour.
Yeah.
40 minutes.
Well, 20 minutes.
It's hours to days percentage.
Right. Yeah. So yeah, this is the mass. Okay, good. I remember why I got confused. This is the mass, but then the actual period of the Isco is bigger by a few orders of magnitude. So the Isco, for a fixed mass, yeah, right. So if you fix the mass of M87, you can ask what is the period of the Isco as a function of the spin. And there's some actual numbers that go in here that depend on the spin. So that would go between 2.5 days and 18 days, I remember now. So the period of the Isco varies by basically an order of magnitude as you vary the spin from 0 spin to maximal spin. So at maximal spin, you get the shortest Isco period, which is 2.5 days. So I guess that's about 5m. No, sorry, not 5m. 5 times, yeah, it's about 30m, right? And then up, and if the black hole is not rotating at all, then the period could be as low as 18 days. Sorry, that's too much. This should be 12 M, and this is about 90 M. Yeah. So yeah, I think one of the things that's very interesting about the experiment in the future is seeing polarization. So for our eyes, light is a wave, has a frequency, which is the color, has an amplitude, which is the brightness, but it also has a direction of oscillation in the plane transverse to the direction of propagation. So we can say the light rate is going this way, but is it propagating like this, or is it propagating like this, or like this? And of course, our eyes don't actually really see that feature, although if you have sunglasses, polarized sunglasses, you look at the surface of the Charles, you'll be able to see or not see the light reflected off of the water. But from the perspective of the Event Horizon Telescope, all these features of the wave are on equal footing. It's measuring all aspects of it. I think they haven't released the polarization yet, but I think they plan to in the coming year. And that's very interesting because it'll be able, if you add in some physics, you might be able to say that the polarization is, say, connected to the magnetic field. So we'll be able to learn about that. And then I think another thing which is really exciting is that not taking pictures, but filming a movie, so having pictures over time, many, many frames. And then if you see patterns that start to emerge over certain time scales, now that you know the mass, this is the point I was trying to make, but I didn't remember numbers. If you know the mass of the black hole and its characteristic length scale, if you see a signal with a certain time variability, and you say maybe that's the Isco, okay, then you have to add in some more physics. But if you were to see a periodic signal from the Isco, well, then depending on how many days the period lasted, you'd be able to infer something about the spin of the black holes once you know its mass. So I think that's also another exciting frontier. Okay, I've really.
More questions for Alex?
Jets are also a source of background light for the shadow, right? Can we, in principle, identify that features in the photograph that you show that like correspond to the jet? It just looks like a stream of light with no kind of linear features.
So we already have pictures of the M87 Jets. I mean, I don't want to be glib, right? But if you Google M87 Jets, okay, some of these are fake pictures, but some of them are real pictures.
Artist conceptions.
Yeah, that's a real picture. So what's the difference between this and the event? You're unhappy now. You're frowning. So what's the difference between? Well, what's the big deal with M87? We already saw the Jets. So this scale here is on the order of millions of light years. So on this picture, the black hole, the event horizon, the shadow, it's not even a pixel. It's microscopic here. So we can see the Jets, but I think the frequency at which the Event Horizon Telescope is observing, this isn't the X-ray, it's Chandra. So that's looking at light that has a much higher energy or frequency. And one of them is radio. Okay, so yeah, that's right, VLA. All right, well, the danger when you Google things during a lecture is that you don't know what you find, but yeah.
Well, I think they don't know the answer to that question.
It could be electrons continually accelerated. That's another possibility. Accelerating charges radiate, which I think is one of the explanations that I've seen. But okay, why is it being accelerated far away? Yeah, that must be another effect too. I think the statement is that we understand the physics more or less that locally extracts energy from the black hole. So the black hole, there are magnetic fields that have a pointing flux vector near the poles. So there's energy flux from the event horizon of the black hole. And as a result, the black hole spins down. So that happens through the electromagnetic field. But now, what's actually in the jet? How are particles in this jet loaded onto it? What's the mechanism for loading particles onto the jet? I think that's an open problem as far as I know. I mean, you can do numerical simulations, but that can give you some idea. Oh, and last thing, I'm just going to flash this. I thought this is cool. So I thought the first two questions by journalists at the conference were sort of like, do you have like a sharper image? Or and, you know, like, oh, is it going to get better over time? Why is it blurry? And I thought, come on, guys, you're sort of missing the point. I just thought, you know, we're seeing a grain of sand from the airplane, the quarter in LA from the East Coast. So, you know, people are a little too tough, I think. And you know, now they can do it. The first time you do something, it's a physics experiment, and then the subsequent iterations are an engineering experiment. So, you know, now you can just throw more money, better clocks, more hard drives. You know, now we know it works, so it'll just get better and better. Okay, and I'm cheating because apparently we sent a satellite to Pluto. So don't expect that either, you know, but it's just proof of concept. Okay. Okay, you'll never get to the Kerr Metric, so.
Okay, maybe I'll. Do we need a 3-minute break, or should I just? All right, I'll just lecture. All right. Okay, so can we? Let's see. How do we get this? No. Do you know how to do that? Left screen.
Here, I got it. Okay, good. Thank you.
Okay, but now we need the right screen off too. Let's see. Do you know how to get these lights on? Thank you. Okay, so that's all a lot of fun. Just one thing I wanted to add is that when you get to one of, because we've been having this discussion about, you know, fixed points and black holes, and if you look outside the black hole where the jets are, and there's all around it, there's all this plasma and all this complicated stuff going on that is really interesting to try to understand, but it's certainly very complex. But right at the center, black holes are these incredibly simple objects that are described by these exact solutions, which we're going to write down today. And that's why it's so exciting, at least to me, to like that they finally have an image where they've zoomed in and there's that central object is coming into, you know, visual focus. And I think the coming decades is going to see, you know, ever increasing resolution of these images and ever increasing understanding of what's going on. All right. So two things I'd like to do in the next half hour. I want to talk about this one more important aspect of Riesner-Nordstrom, and then hopefully I'll have time to write down the Kerr metric. So we discussing the Reissner-Nordstrom metric, which is R minus R plus, R minus R minus, T squared over R squared plus dr squared times R squared over R minus R plus, R minus R minus, plus R squared, the omega squared. So now there's an important property called the surface gravity, which I want to discuss. And the surface gravity can physically be described like this. So here we have the black hole. This is the event horizon at R equals R plus. And now let's say we're out at infinity, and we have a rope which can't be stretched at all, but also doesn't weigh anything. And we hang a mass on it, and we ask what force do we have to exert? So we have some object of mass mu, which we dangle at the end of our rope. And if this object is we ask the question, how hard do we have to pull? How much force do we have to exert to keep the mass dangling at a fixed distance from the black hole? Now, right now, if ignore the gravity of the Earth, but Sagittarius star, very far away. If I had a mass at the end of the rope, I wouldn't have to pull very hard because we're so far away. This Sagittarius star is not producing a very strong gravitational field here. Okay, the Earth, of course, dwarfs its gravitational field. But you might think that that as if we let this mass mu get right to the event horizon of the black hole, that there would be a limit that we would have to pull because the force of gravity gets so strong. We might think that the force that we would have to exert would be infinite in order to keep it dangling just infinitesimally above the horizon. But in fact, it turns out to be finite because there are two competing effects. The force of gravity is getting stronger, but the energy of the object is getting redshifted as we lower it down to the black hole, and these things cancel, and actually the force that we would have to exert up here to keep it dangling a nanometer above the horizon actually approaches a finite value, and that's known as the surface gravity. And it's defined, the surface gravity as kappa, is defined as the force we would have to exert here, infinity, over the mass mu of the object that we are trying to keep hanging there. So, let's compute this surface gravity for Reissner-Nordstrom. So Reissner-Nordstrom has a killing vector zeta, which so zeta mu d mu is equal to d by dt, and that obeys, of course, the killing equation, d mu zeta nu plus d nu zeta mu equals 0. Now, one thing to notice here is that this killing equation, if we take zeta and multiply it by 17 everywhere, it still obeys this equation. So what fixes the size of zeta? Well, if we multiply it by 17, we still have a killing vector, but we want to choose the normalization so that zeta generates unit time translations out at infinity, far away from the black hole. And this is going to be important later, this arbitrariness in zeta. So now, the form momentum of a test particle moving on a trajectory u alpha, so let's let u alpha equals dx alpha d tau, where this is the proper time along the world line of the particle, that will obey u alpha equals -1. And so now let's define v squared, because p squared is minus mu squared for this particle. So let's define v squared is equal to the norm of this killing vector minus zeta alpha, which is equal to g minus gtt, which for this metric is just the t, the coefficient of dt squared up there. And then the energy, so in general, whenever you have a killing vector, if you have a geodesic and you take u alpha, zeta alpha, it's easy to show using this equation here that if you have something moving on a geodesic, that this quantity will be conserved. So for every killing vector, as we would expect, for every killing vector in any geometry, there is one conserved quantity. And since Riester-Nordström has 4 killing vectors, d by dt, and then the 3 angular ones, geodesic motion in Riester-Nordström will have 4 conserved quantities, the 3 angular momenta, and the energy. So the energy is the one associated by d by dt. That's the one we're interested in now. And Alex was, maybe they're written up there, but yeah, this is related to the, well, the lambda is some combination of this, and the Carter constant is a different animal, actually, which we'll discuss later. But the energy is just equal to minus the mass, u alpha, zeta alpha. And so, so if the particle is held fixed, then u alpha is equal to 1 over v zeta alpha. So for this guy held at a fixed position, obviously it's world line, tangent vector, it's not moving, so it's just d by dt. U alpha is 1 over v zeta alpha, and this v is needed so that u alpha is minus 1, because otherwise it would be v squared. Okay. So now, what is this force at infinity? Well, the force at infinity is equal to the norm of the gradient. It's in the radial direction, the gradient of the energy. But from this equation here, we see that the energy is equal to mu times v. So I've just said in a very careful way, something which is maybe a little bit obvious, that first of all, if we're out at infinity, V is just 1. That's how we fixed the normalization of V. Right? We wanted this killing vector normalized to 1 out at infinity, and the energy for a particle at rest is equal to the mass. Okay. Now, when it's closer and closer to the black hole, it's getting redshifted. Its energy is measured out in infinity. It's getting lower and lower. And how much is it getting lower by? Well, it's getting lower by this factor V, which is really the square root of GTT. And that practically by definition, is going to 0 at the event horizon. But this is equal to, so this is equal to mu times the gradient of V. So looking now at the definition of this, we see that kappa is equal to the gradient of V. And we can also take kappa squared, and we can use the formula for covariant derivative and write this as minus a half d alpha zeta beta d alpha zeta beta. Okay, so this is another many ways of different formulas that one sees for the surface gravity, and this is well, okay, so this is one of them. Now, notice, however, that the surface gravity defined at the surface of the horizon, it refers to infinity. In a sense, it's a local property of the horizon, but it refers to infinity in its overall normalization. Okay, so any questions about that? Okay, so now let's compute this for Riese or Nordstrom. So we have V is equal to the square root of minus GTT. And so the gradient of V will be equal to, so it depends only on R. So we'll get basically square root of G upper, well, the gradient of V squared will be equal to G, the whole thing will be equal to GRR, the square root because I'm taking a norm there, dr square root of minus GTT, dr square root of minus GTT. But then G upper RR is the same thing as G lower TT. They're the inverses of one another. So the whole thing just becomes minus a half dr GTT of course, I'm evaluating this at r equals r plus. And now let's look up at that formula GTT. GTT is r minus r plus, minus GTT is r minus r plus, r minus r minus over r squared. And we want to take dr of this. I already took the minus sign. I want to divide by 2 here. And, okay, we have to act on all these things, but at the end of the day, we're going to evaluate it at r equals r plus. So it will be 0 unless we take this derivative right here. And so the whole thing becomes r plus minus r minus over 2 r plus squared. Okay, now for Schwarzschild, so for Schwarzschild, r plus equals 0. I'm sorry, r plus equals 2m, r minus equals 0. And this becomes kappa is equal to 1 over 4m. But more generally, for Riesner-Nordstrom, using the formula r plus and minus is equal to m plus or minus the square root of m squared minus q squared. Kappa rn becomes the square root of m squared minus q squared over 2m squared minus q squared plus 2m square root of m squared minus q squared. Now, the interesting thing about this formula is that it goes to 0 for, in the extremal limit, m goes to q. And we could have seen that, back up there because you have a double 0 at r equals r plus for an extreme black hole. So even if you differentiate once with respect to r, you still have 0. Now, this is a very important fact. A little later, by the way, we'll also see that when we discuss the Kerr solution, we'll also see that there's a critical point for Kerr when it's spinning very rapidly with the surface gravity, which takes a little more care to define, where the surface gravity also goes to 0. And indeed, we're hoping, though we don't know yet, that they're going to report a very high spin for M87. Probably learn that by tomorrow or something, or maybe it's already been put out today. But why is this interesting? Okay, now I'm going to make some, we violate causality in a, I've been wearing this thing. We violate causality on a regular basis in this course. And now I'm going to make some acausal comments about why this is interesting. Well, the surface gravity is a measure. It's the force. It's a force divided by a mass. So it's the measure of the acceleration at the horizon of the black hole. And there's a very close relationship between acceleration. So kappa is like an acceleration, which is like a temperature. So this is obvious because it's force divided by mass. And these things have the same units when up to a factor of h bar. And in fact, it's a very simple thing, which we're going to not get to until next semester because there's so many interesting things before we get there, that temperature and acceleration are the same thing in quantum theory. And it's just a rather simple fact of free field theory that if you take a detector in free field theory and you undergo it a constant acceleration, that the levels of the detector will get populated with a thermal distribution, which is equal to the acceleration over 2 pi times the factor of h bar, which is needed to make this dimensionally correct. And since acceleration is the same as the surface gravity, we have a formula that looks like this. Okay, so the temperature, we should think of the surface gravity. It's acceleration at the horizon of the black hole, but by some what now seems like, I've just secretly written down the formula for the Hawking temperature of the black hole, but by now what seems like a rather elementary analysis, this means that we can think of this surface gravity as a temperature, and indeed we will see that it is the physical temperature of the black hole, that it does radiate at this temperature. So, but that of course is only in the quantum world, which we haven't got to yet. But again, we see this sort of quantum stuff hidden in the classical equations of GR. And it's often true in condensed matter. We've been talking about these extreme Reissner-Nordstrom black holes as critical points. And it's often true in condensed matter physics. It was always true. I don't know, I'd never say always, but okay. That there's a tendency for critical phenomena to occur at zero temperature, or to be associated with zero temperature. Many materials become superconducting at zero temperature, and lots of interesting things happen when you cool something down to zero temperature, and it becomes easier to understand their structure. It's easier to understand the structure of matter at zero temperature than it is at finite temperature. There's a lot more things to keep track of. So these extreme Reissner-Nordstrom black hole, was long known that their surface gravity, the surface gravity goes to zero on that limit. And since Hawking's work in the 70s, this can also be identified with the temperature. So this is sort of the way the way we now think about these extreme Reissner-Nordstrom objects, and also their extreme Kerr analog, one of which we may have seen this morning. But if we didn't see it this morning, there are other ones out there that we have seen that are extreme, many of them, and not with this resolution. We've seen them more indirectly. But they're zero temperature objects. They're like ground states. If you let the thing radiate all its energy, what it settles down to is this extreme state. We'll understand that. I mean, what I've given you here is a mathematical definition and derivation of, there's a line here. This is future lectures. Up to here, this is a mathematical definition and computation of the surface gravity. I'm just letting you know now that at some later point we'll be understanding this in terms of the Hawking temperature of the black hole, and that we'll understand the extreme black holes as very special ones that are in their ground states. They're the simplest black holes. Wow. It's just going to make me feel a little better if I write down the Kerr metric in the last 5 minutes. It may not make you feel better, but it's going to make me feel better. But we had a great discussion today, so it was worth it. Special day. All right. So here is the Kerr metric, which I will write down for you again next time. It's a solution, exact solution of the Einstein equation written down by Roy Kerr in 1963. And he's a happy man today, I assure you that. Because it's the first, well, they seem to be pretty confident that the thing is spinning, and it's the first time that, you know, the solution that he found more than 50 years ago was really directly seen. Okay, so much more complicated structure. I'm going to find two objects in here. Rho squared is equals r squared plus a squared cosine squared theta. And where this is going to be, A is going to be the angular momentum J of the black hole divided by its mass m. It's just convenient to write it that way. And I'm also going to introduce a quantity delta, which is r minus r plus, r minus r minus. I could have defined delta over there. Didn't really need to. But with Kerr, the formulas just get so long, you have to introduce some extra symbols. And where r plus and minus are, again, the inner and outer horizons, it's amazing how similar it looks to Reissner-Nordstrom at m squared. Now, instead of minus q squared, it's m squared minus a squared. And so we have dt squared plus r squared plus a squared plus 2a squared mr over rho squared sine squared theta times all times sine squared theta d phi squared. Ran out of space there. This multiplies that. And then plus, plus rho squared over delta dr squared plus rho squared d theta squared minus the infamous cross term 4a mr over rho squared dt d phi. Okay, so this is the famous Kerr solution. Very hard to show that this is a solution. When I teach general relativity, it's too long to Schwarzschild, I work it out, show that the Einstein equations are obeyed. This certainly does obey the Einstein equation. Nobody has a very simple derivation of it. I don't know anybody that, when I teach general relativity, it just would take a couple of lectures and everybody would be falling asleep to show that this is actually a solution. Maybe someday well, I would pose it a challenge to one of you to find a way to demonstrate that this is solution in less than, I don't know anybody who does it when they teach GR, but it's definitely true that, that it is an exact solution. You got a fast one, Alex?
You can get it by coordinate transformation from Schwarzschild, which is complex, like this magic. I always am aware of this.
Okay. Maybe I'll get Alex to do it. Okay, I probably don't have time to do much with it, but there are all kinds of interesting things going on here. In addition to the singularities in delta at so this coefficient becomes infinite when at either the inner or the outer horizon. But this is behaving a little differently. These terms conspire in a complicated way so that the horizon, the outer horizon, is still a smooth surface. And then you've got this term. Let me just say that one thing, that this solution is not invariant under either t goes to minus t or phi goes to minus phi, but it is invariant under a number of other things. Like if you take t goes to minus t, let's talk about t goes to minus t and phi goes to minus phi. Then the solution is invariant. Now, if you have something with angular momentum and you run the movie backwards, it does this, and then you take phi to minus phi, it does this again. So that's exactly what you would expect for something with angular momentum. Alternately, if we take either t goes to minus t and a goes to minus a, or phi goes to minus phi and a goes to minus a, then it's also invariant. That is, if we run the movie backwards and then change the sign of the angular momentum, we get back where we started from, or we change it. All right, so this has all the right discrete symmetries to be a metric associated with something carrying angular momentum. And indeed, a more lengthy analysis, which I probably won't give, shows that it carries angular momentum J equals ma. Okay, I'm going to stop there.